If we think about finding the limit as x goes to 3 for this function, f of x, we can see pretty clearly that the limit doesn't exist, right? Because if we start to the left and slide towards 3, the corresponding point on the graph goes up and towards height 3. If we start at the right and head to the left towards 3, the corresponding point on the graph is heading towards height 2. So this limit does not exist. But you know, the reason that it doesn't exist, it's not that approaching from one side or the other is problematic. It's just that the two sides don't agree. So, you know, you might think, well, why don't we just throw away one side or the other? Why don't we just concentrate on one side or the other? And we can do that. And that's the idea of a one-sided limit. So in some situations, it doesn't make sense to approach your number from both sides. Sometimes you only want to approach it from one side. An example of that would be, say, in special relativity, where the speed of light c is sort of a universal speed limit, and you can never go faster than c. Well, if you want to know what happens as something approaches c, you don't care what happens if it approaches c from above. You only care what happens as it approaches c from below, because, you know, whatever object you're talking about, it's not moving at the speed of light yet, and so it will be approaching the speed of light from below if it's speeding up. So, and there are other situations in applications where you don't care about a limit on both sides, you really only care about a limit on one side. So let's modify our notation for limits to indicate which side we're approaching 3 from. So if we want to approach 3 from the left, how should we change this notation? Well, the way that we'll change this notation is we just need to indicate that this 3, we aren't approaching it from both sides, we're only approaching it from the left side, but the left side is sort of the negative side of 3, so let's put a little negative right up here. This is a sort of a superscript on the right-hand side of 3. So this indicates that we're approaching from the left. And you can, so now we don't have to worry about what happens from the right. We're only looking at the red arrows here. And from the left, on this graph, as we approach 3 from the left, the graph is going towards 3. So this is a one-sided limit, and it exists even when the regular limit doesn't exist. All right, well, the other way we could approach x equals 3 is from the right. How should we modify our notation for that? Well, clearly, I guess we should put a little plus up here because the plus side is to the right of 3. So f of x. So now we can only look at the green piece and ignore the red stuff. And as we approach from the right, the corresponding point on the graph slides towards height 2. So this limit would be 2. All right. So you can see that these one-sided limits can exist even when the two-sided limit, or the original limit, doesn't exist. Let's look at a couple examples. Let's find the limit as x goes to 2 from the left of 1 over x minus 2. Well, there are a couple ways to do this. First, we can do this graphically. So if we just sketch a graph of 1 over x minus 2, right, that looks like 1 over x, but it's shifted to the right 2 because of the minus 2. So that's going to shift this vertical asymptote over to 2, and it's going to look like something like this. Okay, now we're going to approach 2 from the left, so that means we should start here and then slide rightwards, and you can see this is going down to minus infinity. So this limit is minus infinity. Another way we could do this is we could take this expression that we're taking the limit of, 1 over x minus 2. We are going to 2 from the left, and that means that this x value is a little bit smaller than 2, right? So what we could do is plug in 2, but a little bit smaller than that, so with a little minus sign right there. And this little minus sign isn't a negative, it's just reminding us that what we're plugging in isn't 2, it's a little bit smaller than 2, a little bit more negative than 2. And now we can do some arithmetic here. So if we have something that's a little smaller than 2, and we subtract 2 from it, what do we get? Well, we get something a little smaller than 0. And what's 1 over something a little smaller than 0? Well, that's negative infinity, right? 1 over a tiny negative number is a negative huge number, so negative infinity. You can see either way we get the same thing. All right, for another example, let's find the limit as x goes to 0 from the left of x over the absolute value of x. Well, the absolute value is a little tricky to handle because remember the absolute value is, it's just x itself if x is greater than or equal to 0, but it's the negative of x if x is less than 0, right? This negative, right, if x itself is negative, this extra negative sign flips it so that it's positive. So negative, if x is negative, negative x is positive. So this multi-part function is one way of thinking of what the absolute value function is doing. And since we're approaching 0 from the left, x is actually always negative in this case, right? Because we never actually get to 0. This limit, when we're evaluating this limit, we're never at 0, we're near 0. And since we're approaching 0 from the left, we're near 0 but negative. So that means that for the purposes of computing this limit, we are always in this second case. So we can replace this absolute value with just negative x. So now we have now we can simplify this. X over negative x is minus 1. So the limit as x goes to 0 from the left of negative 1. Well, you know, this graph, the graph of this function, looks like this. So as we approach 0 from the left, the corresponding point on the graph does this. So we're just going to get minus 1. All right. So there's a pretty clear relationship between one-sided limits, right? In our first example for one-sided limits, we said that the two-sided limit doesn't exist because each side, right? Each side exists as a limit, but they don't agree. Well, if each side exists but they did agree, that means that the two-sided limit would agree, and that is how it works in general. If you have a two-sided limit that exists, then that means the one-sided limits both have to agree and be the same. And vice versa, if the one-sided limits exist and are the same, then the two-sided limit exists and has that same value. And we can use this to evaluate some tricky limits where there's some sort of weird thing happening at this junction point, our value for a here. And this is often something that you need to do when you're dealing with multi-part functions. So as an example, let's find the value of the limit as x goes to 2 of f of x, where f of x is this multi-part function. It's really sort of tricky to know how to start for the two-sided limit because, right, since this function essentially has two formulas, there's sort of no single holistic way to deal with what this function is doing. But what we can do is, instead of asking about this two-sided limit, we can instead ask about each one-sided limit individually, and then compare our results and see if they match. So let's calculate the limit of f of x from the left, so the limit as x approaches 2 from the left, and we will also calculate the limit as x approaches 2 from the right. Now the advantage of doing this is if x is approaching 2 from the left, that means x has to be less than 2. And that means that we can use the first formula here. So we can take the limit as x goes to 2 from the left of 1 minus x. Okay, and correspondingly for the limit from the right, well, if x is approaching 2 from the right, that means x has to be bigger than 2. And so we can replace f of x with this second formula because that's the formula you use when x is bigger than 2. So x squared minus 3. Okay, now for each of these individual cases, well, I guess really the only way we have of evaluating these limits is to look at the graphs. So 1 minus x, that's a line. Y-intercept is 1. slope is -1 like this. Oh, sorry for the wiggly line. Like this. That's a little better. And it looks like, so if we start to the left of, sorry, not 3, 2. If we start to the left of 2 and head towards 2, we're going to slide down to here. And if we, you can see that the height that this point is sliding towards is actually just the value of this function at 2, and that's -1. Okay, so how about x squared minus 3? Well, x squared minus 3, that's our standard parabola, but down 3, so 1, 2, 3. So something like this. Again, so we're starting to the right of 2, so if we start over here and head towards 2, you can see again for parabolas, the value that this point is sliding towards is the same as the value of the function at this point. So we can actually just plug in 2 here, and we get 1, it looks like. Well, look, these are different, right? This picture actually isn't accurate at all. These two one-sided limits, they both exist, but they're different. And so the two-sided limit, the limit as x goes to 2, does not exist. If we changed this formula a little bit, it looks like if we changed this to a 5, then this would actually come out to a -1, and then these would agree, and the limit would be -1. But as it stands originally with the 3 here, since these disagree, the two-sided limit does not exist.